I'm Stephan Eckes, and I want to talk today about building audio apps with Rust. So we won't focus so much on the language itself. There are a lot of great talks about this. I want to focus more on the whole ecosystem and where we are with building actually audio apps, how to access the system audio, how to build plugins, how to write your UI. So yeah, you can decide for yourself if that's something that you already want to go into, or if the feature set isn't enough for you already. So shortly about me, I studied audio communication and technology at Technical University of Berlin. Here are some people as well from my course. It was very nice to study that. And during this time, I was working as a working student for Neumann, UHE, and Toloplot, where I learned real-time audio development in C++. So great time. I learned a lot there. And at Toloplot, I was actually introduced into Rust. We changed the project from C++ to Rust and got the chance to learn a lot about the language. So now I have around about 3 years of professional experience in Rust. And currently I'm working at AI Acoustics. There I'm responsible for the SDK and our inference engine. So what we do is real-time speech enhancement from microcontrollers to desktop devices. And yeah, I have to build a lot of demo applications and devices. And it's nice that I can use Rust for Cortex M7, but also for Android and for macOS and Linux and Windows. Yeah. And with NeoDSP, that's my weekend project where I just try to publish some libraries. It's mainly for now just I publish some stuff that I built in my free time. And I would like to build a little YouTube channel to talk some more about DSP. And maybe a valid question, why do I like to speak about Rust? I just felt that during all the time where I had to build so many different applications and mainly worked as a solo developer in my startup. So I had to create apps. I had to create a lot of different apps in a short time. And with Rust, it was just possible that it's really reliable. And I don't have to care so much about building all the ecosystem. So make and CMake projects, integrating test frameworks, and could take more time to actually develop the product. And if you want to follow the slides, you can grab your copy here. All the underlined stuff, or the underlined text is a link actually. So if you want to check out a project that I'm mentioning, you can just click on the link. So when we want to build an audio app, at least a standalone audio app, the first thing you need to integrate is the system audio or the system audio API. And yeah, as this is the core of your application, I want to start with that. The first option we have is using platform-specific APIs. So this is basically just a wrapper of the C APIs from ELSA, Jack, Pulse Audio, Pipewire on Linux, but there's also a wrapper for Core Audio, Wasapi, ASIO, Oboe, and Android. So there are basically all the APIs we need are accessible, but maybe not every feature is implemented yet, or not for every function there's a wrapper, but they are quite thin. So even if one project would be a single maintainer project, it's something you could still maintain yourself, kind of, because most of that is auto-generated and you can directly call into C very easily. But if you want to make your life a bit easier, you can use platform-independent APIs. If you want to have higher level functions or don't want to care about every system itself, there is port audio, RT audio, CXX juice. Those are C bindings. Those are using the C bindings. With Juice, the build process is obviously a bit longer, but I think most of you know this audio I/O callback. It's quite reliable and has quite a low latencyy. And port audio was so far the most reliable wrapper I was using. It's quite nice. It has duplex streams. And there are some projects that are mostly in Rust, like CPEL is the biggest project at the moment. It stands for Cross-Platform Audio Library. With pure Rust, I mean, it's pure Rust besides the direct system API like ASIO and so on. There's nothing in Rust yet. so the driver would need to be implemented in Rust to be possible. But CPAL especially has web and mobile support, what is quite nice, but there are no duplex streams. So in my applications, I couldn't use it that often because you just get an input audio callback and an output audio stream, and you need to synchronize that yourself. And as some of you might know, that's quite complex, and especially if they don't run always at the same clock, you have to add some latency, and you possibly won't achieve such a low latency as with a direct duplex stream of port audio or RT audio. And QBAP is the backend of Firefox. So it's quite reliable, but it's not really made for super low latency audio. For example, you can't select the frame size. It's just giving you a best effort frame size. I mean, you could work around this with an adapter, just like buffer some audio to get your frame size you need. But yeah, you cannot select a lower latency than the one you will receive. For example, just a code snippet, I don't know if it's readable, but with port audio, you just create a duplex stream and you have a callback-based API. In Rust, the stuff in between the pipes is a closure, so it's like a lambda in C++, but it can capture its environment automatically. And then you just open this duplex stream, so it's quite easy to use. But I also wrote a little wrapper for this. It's not meant for production necessarily, but if you want to check out, I integrate some different frameworks there and made an easy API because I wanted to be able to test out different wrappers and make it quite easy to switch that out in my apps. And especially you will find a nice example of integrating a complete audio settings menu in 3 different front-end frameworks, so web UI and 2 native UIs. And yeah, settings menus can get quite complex when you want everything to be updated in real time and that you get the new channels when you change the device and the audio stream gets automatically started again and so on. But in eGUI and ICE, I implemented that if you want to have a look. And it just works like this. So you open Neo Audio with one of the backends you choose, and then you can just start it with your processor. There you just implement the processor trait that has a process and a prepare function, and then a sender is returned for easy commands, so you can just send thread safe messages. Also, you can check the available output devices or set and get the device. And those are the 3 test UIs I implemented. So the left one is eGUI, in the middle you see iced, and at the right side there's Tauri. Makes it possible to build web UIs, desktop apps with web UI. But yeah, to actually integrate your audio streams into a front end, we need to learn a little bit about thread synchronization and how this is possible in Rust, which tools we have. So one directional synchronization we can achieve through channels. That's like the most used thing in Rust. It's very easy to use. You have a non-blocking option, but there are some limits in performance. So it's a queue, and it's better for if you don't want to send streaming data or like a lot of data in the end. But it can be multi-producer, multi-consumer. So there's one in the standard library that is quite nice, but it's only multi-producer and single consumer. And especially in audio, you would like to have a bounded option. So the Crossbeam library is the biggest, one of the biggest thread synchronization libraries in Rust. It's used in a lot of applications, so it's quite stable. And there is a bounded channel. So you pre-allocate the maximum amount of messages you can have in the queue, and the performance in general is better. At the right, you see it's very easy to use. So you just create a bounded channel. You will get a sender and a receiver, and those you can clone as often as you want and just push them in any threads you want to have them, and then send and receive. And you will also find try send and try receive functions, and those are the non-blocking options. They might not return something if if there's no message in the queue or so, but they won't block and wait for a message. And especially with this function try iter, you just go non-blocking through all the messages that are in the queue and can process them. So that's what you could use in an audio thread. And because the execution time will be bounded, as the queue is maximum, for example, 1,000 messages long, that's the maximum time you have to wait to go through all the messages. The second option is a ring buffer or FIFO. There's a really nice crate called ring buff. It's quite flexible, so you have a local option, a shared option, and you can choose if it's static or on the heap. Ring buff is completely lock-free. It's quite simple to use. So ring buffers from C++. It's good for audio data, like sending something to the level meter, where you're interested in every bit of the history. But they're also only single producer, single consumer, so they only work for this. And a second nice library is RTRB. That's the real-time ring buffer. In some cases, this is faster, but there's only one type, so only the shared heap version. It works exactly the same like channels in the implementation. So you get a producer and a consumer. You can put them into different threads and push or pop. Push to the producer and pop from the consumer. And the last thing I want to show you for one-directional synchronization is the triple buffer. That's just a double buffering implementation. That's nice if you only want to have the newest update available, so for a spectrum or for an oscilloscope. This is as well only single producer, single consumer, and it's completely lock and wait free. So you will find it also in some of the plugin frameworks that it's used for spectrograms. Then for shared memory, obviously the easiest thing you can use is a mutex. I don't have to explain you mutexes possibly, but what is nice about Rust is they automatically unlock when the guard goes out of scope. So a mutex, when you lock a mutex, a guard is returned, and as soon as your function ends or your scope ends, the mutex will be automatically unlocked. So it's harder to generate deadlocks. You can still generate deadlocks. It's not impossible, but it might be a little bit easier to use. But for sure, mutexes block the thread or it fails to get the resource. The other thing that is special is that in Rust, in the standard library, the mutex returns a poison error. And this poison error is just indicating that a thread that was holding the lock was panicking. So it's fine when it panics. It still return the lock. You will still get the value back, but it's just an indicator that the value you will receive might be not right because the thread couldn't finish its execution. There's a mutex with better performance actually. It's the parking lot mutex. It's also a quite often used library. But this one does not return a poison error. So in the API, it's a bit easier to use. But if you're interested in this poison error, you should go with the standard library mutex. There's a little example. So if you create a mutex, your variable does not to be mutable because you have interior mutability in this case. And the lock function blocks the thread and the try lock function does not block. But I'm not 100% sure if I don't think it's necessarily wait free, but it might be short enough to call it in an audio thread. What you really need to understand or at least what you always have to use to work with mutexes or even atomics is rich pointers. You have three types in Rust. There's the box, the RC, and ARC or ARC. It's actually kind of easy. They sound more complicated than they are. Box is just a pointer to the heap. So you use that when you want to, when you have an object where you don't know the size at compile time. And the RC is just a pointer with a reference counter. So the reference counter just makes it possible to clone this pointer, and inside it will just count how many people have a pointer to this object, and if this counter goes to 0, the object can be freed. The arc just implements this counter in an atomic fashion, so you can clone it for free as well, but in a multi-threaded fashion. And multi. This is exactly what you need for mutexes. So you just wrap the mutex in an arc, but when accessing the mutex, like when you call the log function, you don't need to care about this because the dereferencing will be done automatically in Rust. But now, yeah, you can just clone this object and move it somewhere else and have multiple pointers to it. The same you have to use with atomics if you want to share them to multiple threads. But yeah, atomics are obviously a bit harder to use. They only work for very small data. I mean, that's what we use most for audio parameters because it has by far the best performance. And yeah, with atomics, there's nothing really special. They work exactly like in C++, as mostly they just call into the CPU to use the atomic operations of the CPU. In Rust, they are strictly typed. So you have, in the standard library, you have atomics for bool and integer types. If you want to use it for a float, you need to adapt it yourself to a U32 or U64. But there's also a little wrapper around the standard library called atomic float that does this for you if you just want to make it easy. And if you want to implement an atomic for a generic type, like your own struct that just has a couple of integers, you can use the crossbeam atomic cell. This is generic, but there you also have to call the function isLog3 to make sure it works with your struct. Your struct is small enough. And you see atomics are also quite easy to use. So you have you just create an atomic with a new function, and then you have store and load operations. You also have all the fetch, add, and the stuff. But in Rust, you have to provide the ordering. In C++, there's a default, so you can also just call store and load without an ordering. But yeah, the ordering matters. I mean, you can really create bugs with the wrong ordering, but the orderings are exactly the same as in C++, so you can also go and read the C++ specification. They work similar. You have the types from relaxed to sequentially consistent. Relaxed just gives the most freedom to the compiler to reorder stuff, and in some cases that's totally fine to use. For example, if you just send something to the audio thread and nothing else depends on it, it could be fine. You might not get always the newest update, but this in some cases it's totally valid to use. And sequentially consistent has the strongest guarantees. That's also what C++ is using by default. And if you have no idea what you're doing, you might stick to sequentially consistent until you get performance issues or something. But the three in the middle are basically the same guarantees, but release is only for storing a value, acquire is for loading a value, and acquire release is for operations that load and store at the same time. So like fetch, add, when you want to have the load with acquire and the store with release. If you want to know more about this, so atomics can fail. For example, here we have we spin up two threads that add 1 to a value, and in the end we expect it to be 2 because we have two threads, they both get called, they both add 1, but in the end it can be 1, for example, because there's a load and a store operation, but in between load and store the other thread could load, and then both see the value 0 and add 1 to it, they both store 1, and in the end we end up with 1. But it's quite, there you should use a fetch add, for example. A fetch add just makes it in one atomic operation, and the issue is solved. But if you want to learn more about this, the Tokyo Loom documentation is quite nice in Rust, and there's a really good YouTube video called Atomics and Memory Ordering by John Jang-Set. And he's explaining in 3 hours every type of ordering. So that's also nice to watch for C++ if you want to know more about this, because I think most of the people don't really understand atomics. It's quite complicated thought model. Then let's go to some graphical user interfaces. Which options do we have there? Like I said, you can check out this repository to see some examples, and I will show you those 3 UI libraries. For native user interfaces, there's, for example, eGUI. That's quite popular crate, but also kind of a single maintainer. So that's a lot of times the problem in Rust, that you have a lot of single maintainer libraries. But it's getting quite big and quite popular. So you have even some VST plugins that use eGUI. That's the one at the bottom left. Yeah, it might be also good to reduce the lighting a bit or something, right? To see the, I don't know if that's possible. At the bottom right, there are some example applications from eGUI itself. You can also check the demo in your browser. There's a nice plotting library inside, so it's quite nice to use. And Iced is also getting quite popular. At the right, you see there is now a Linux desktop environment that's completely written in Iced. So I don't think it will be dropped too soon. It's the desktop environment for the new Pop! OS from System 76. Or at the bottom, you see there's a VST synthesizer, completely in eGUI. Or at the left, it's just a MIDI visualizer. Also, both libraries I showed you, they are running on GPUs. So they use WGPU. That's a crate that makes GPU code work on different platforms. So it's using Vulkan, Metal, or Web GPU in the browser. The difference between them is mostly eGUI is an immediate mode library. Iced is a retain mode library. So in general, I mean, there's also right now an immediate mode talk happening, I think. Immediate mode is a bit easier to use, might be less powerful or slightly less performant, because you only have the update function, and this is called basically 60 times per second if you have 60 hertz. So the idea is coming from video games where you have to re-render every frame anyways. But this makes it super easy to show your state. You don't need to send signals to components to update the button or something. So your state will always be rendered because you re-rendered every frame anyways. And everything is function-based. So even this button is just a function that you call. It will just create the rectangles it needs to render and return a response. And you can just check this response for, was the button clicked or was it hovered? So you just call if button clicked, you can increase the value. And this gets re-rendered every time, so there's nothing you need to synchronize or send somewhere. It's very easy to use. But Iced, on the other hand, is retain mode, but also has a nice model. It's inspired by the Elm architecture. And that means we have a view function and an update function. The view function has non-mutable state access, so it's really just for showing the current state. You cannot change anything in there. You just describe your UI and give messages to components. So, for example, there's button with an on-press function, and to this on-press function, you can pass a message that should be sent in case it was pressed. And at the update function, you have mutable state access, and there you just receive all the messages. So you can match on this message, matches like a switch case in C++, and then just decide what should be changed in your state when which message is received. And this is a quite nice model because it's giving responsibilities away, and you will always find where something is done, because in your view function nothing can be changed. So you can always just see it in the update function what's happening. And to compatibility, they currently work for Windows, macOS, Linux, and web. So no Android and iOS. I mean, it would be possible, but I guess someone has to build it. And it works for audio plugins. So there's a nice framework, NIH plug, that just implements, that just has examples for those two libraries. Yeah. And if you want to learn more about it, Iced has an amazing third-party tutorial. It's from Fogarish's Iced tutorial, and the official examples are quite good. Also, there's an app showcase on the website, ice.rs. And with eGUI, mainly the feature demo is really nice. It shows every feature that is built into the library. You can also open it on your phone. It renders in WebAssembly. And the official examples are and there's an app showcase in the GitHub repository where a lot of people show what they've done, so you can learn a bit how they implemented stuff. Just as an additional mention, there's also Slint. It's created by former Qt engineers. It works as well on mobile and microcontrollers, but it's using a Qt-style markup language, so you don't work on Rust anymore with describing the UI. And the licensing is a bit more complicated as it's a company, but there's definitely a royalty-free option if you just do it for desktop. And there's currently no official or easy way to create plugins, but some people have done plugins with it, like this from Wes Audio. It has quite a nice UI. But there's nothing public yet where you can just integrate it. I think there's one example that is experimental, but they're on the way definitely, so they want to support plugins for sure. Then there are web user interfaces, if that's something you're more interested in. There is the framework Tauri, which is super powerful. So there are also some audio apps that are built with it, but I mean, I don't have to show you web UI. You can use anything you want. So from all the JavaScript frameworks to there are also Rust frameworks for web UI. And especially nice with Tauri is the feature set. So if you want to create a desktop app, you have so many things already built in that you don't have to care about, like app bundlers for every platform and every Linux distribution, basically, with ready-made GitHub actions that you can just integrate to your project, and it will build, bundle, and notarize your app. There's a built-in self-updater for the apps that you can use. There are sidecars. That means you can integrate Python or NPM into the app if you want. And there's a rich plugin system with stuff like global shortcuts. You can use system tray icons, biometrics like fingerprint readers, NFC, WebSockets. So there are a lot of nice plugins that make it easy to build a complete desktop app. Also like an icon generator where you just add one icon and then it will generate nice icons for every platform. And the app size is minimal, so it's not like Electron where the browser gets built in. It's more, I think, like the new Juice plugins where you use the system web UI. So the app size can be as small as 600 kilobytes. Also, you have some nice inter-process communication built in. So there are commands. This is the default way of talking from the front end to Rust. This is using string serialization to JSON, so it's not the most performant, but it's quite powerful. It can accept arguments and return objects and errors. You can use it for small and large data because you can return a large object with an IPC response wrapper, and then another strategy is used, not JSON string serialization. So it's better if you return a large object, and it can be async or blocking. So you can as well access global state and the app window inside of those Rust functions. And the other tools you have built inside are events and channels. So events are more for data that doesn't happen so often, so more like push notifications or, I don't know, just a notifier that something is finished in the backend. And channels are a bit more complicated to set up, but they are faster and good for streaming data. So download progress or WebSocket messages. And Tauri is compatible to all desktop environments, but as well for Android and iOS. I recently built an audio app for Android. showing our speech enhancement on Android. So I was using the Oboe library and Tauri, and it was so easy to set up. Like I never built an Android app before, and it just worked. That was quite nice. And yeah, that you have bundlers for Debian, Fedora, Arch, and FlatHub is so cool. So you don't need to know all the stuff. You just care about your app and not about all this stuff around it. And there is an experimental project using the Tauri WebView renderer for a plugin. So it's definitely not working perfectly on every platform yet, but there's work done. And check out this project, NIH plug WebView. So you can get started and even try this out. For resources, just read the official Tauri guide. They put a lot of work into it. It's really well written. And there's also this awesome Tauri repository where you see a lot of demo applications if you want to learn how other people solved their problems. Then let's have a look into audio plugins. So the lowest level you can go is directly using the C bindings to CLAP or VST3. They are existing. You have those unsafe bindings to the C API, which gives you obviously the highest level of control, but it's difficult to write and it's not very rusty. So usually we don't want to use raw pointers in Rust. But here you see in this function, there are a lot of raw pointers involved as it's directly calling into the C API. For CLAP, there's also a quite low-level wrapper that just makes safe bindings out of this unsafe API. And this is called CLEC, and it enables you to make a host and plugins. But if you want to use something easier, there's an amazing framework called NIH plug. It's a complete plugin framework, so you have 3 UI library choices that are kind of wired up with examples. There are many features like thread-safe parameters, parameter smoothing. It automatically stores the plugin state, for example, without you doing anything. So you just tell which parameters you want to have. You can even have hidden state inside of those parameters, and they will be automatically there again if you restart the plugin. And optionally, there are cool features like it fails to compile if the process function allocates memory, what is especially nice if you haven't used Rust before and you're not really sure about what is actually allocating memory, or can I call this clone function or not? Is it just cloning a pointer, or is it cloning a whole object? So that's quite nice to get started. And yeah, the example plugins are super well documented, and also all the functions are just very clear to understand when the reset function is called, for example. And it's hard here to read the code in this dark mode, but it's kind of easy. You just have the my parameters. You just create your parameter struct, and then you give an ID to every parameter. There are float parameters, bool parameters. And also stuff is built in like float ranges that are skewed. So for logarithmic representation in the plugin of your linear value. And then you have this builder pattern where you just call with smoother, with unit, with value to string function. So for me, it was such a blast because it was so easy to get started with a plugin. Then you just implement this plugin trait. Where you have your metadata and your audio I/O layouts, so you can just describe which layouts you want to support. And then this initialize, reset process, and deactivate function. And the rest you have to do is just implement the clap plugin trait with the clap specific stuff. So like the clap description, the clap features, and the VST3 plugin trait for the VST3 specific stuff, like the subcategories. And in the end, you just call this macro, export clap or export VST3. Macros in Rust are very different to C++, so they just generate code that also gets checked. Those macros just make it possible to export the actual plugin. And the only problem we have is audio units and AAX plugins. There's no direct way to do it. Maybe you could build an audio unit with the core audio API. I'm not sure if that's made public there. But yeah, there's no direct wrapper or no simple example to get started with it. The simplest solution for audio unit would be right now to build a clap and use the clap wrapper. This can create a VST3 audio unit v2 and standalone plugins out of your clap plugin. But yeah, the clap wrappers are loading the clap plugin dynamically. So the clap plugin needs to be in the right location for your audio unit to work. That might be not the easiest to communicate to your client, but it definitely works well. I tried it with the NIH plug framework. And then we can get to some cool debugging tools. How can you debug your Rust code? The nicest thing is built-in tests. For me, it's just so much nicer that you write a function and immediately have the test underneath the function. So it's just like that. When it's more accessible and less effort, people just write more tests. And you can even say, you can even bring in dependencies that will be just used in tests. So that's still possible. You don't need to include this in your main release build. And yeah, there's really no complicated setup. You can still do tests in other files like integration tests, but just that it's possible to have the tests built into the file and call cargo test. I mean, that's kind of similar to other languages like Swift and so on, right? Or Zig, but I think it's a very big plus. Then stuff like assert no alloc that you can pull into your tests. That's I guess that's the same that NIH plug is using. So with assert no alloc, you can just say you can just call a function, and inside of this function you can say what you want to do. And yeah, this will just check that your code doesn't allocate. But beware, it's only working for Rust code. So if you're calling into the C++ library and this is not using the Rust allocator anymore, it won't warn you. So for example, if you call, I don't know, I recently for machine learning, I had to test if those open blast libraries and so on are allocating memory. This can't help you there. But yeah, especially if you're new to Rust and you want to learn which types allocate, and in general to have this in the CI/CD pipeline just to make sure that no one builds something into the process function is really nice. Then benchmarks are super easy to integrate. There's even benchmarks are built in, so you could even make them in the same file, but that's still unstable in Rust. It's in the nightly feature. In stable Rust, you can use Criterion. That's more powerful anyway, so it creates HTML reports. It has a history, so you see if your code improves over time. And yeah, it can still be run with a built-in cargo bench command. And yeah, it's just in general super easy to set up. So here you see this code was 10% improving in performance. It's all green, cool. So you can slowly check what is working better on your architecture. Then cool crates like Quick Check. Quick Check is a property testing or fuzz testing tool. And what is the nice thing about it is you just have a function that you annotate with a Quick Check macro. And then every input you give to this function will be automatically injected. So if you say, I need a vector of floats for this function and maybe an unsigned integer, it will automatically be injected with random values, and you can test your function for it if it withstands every one of those values. You can also make some guards, so this function is just returning a bool. If you want to say, okay, this array has to be smaller, just return true in the case you don't want to call your function with it. And it's doing automatic shrinking, so it tries to find the simplest input where the failure of your function still happens, so it's easier for you to debug. Then we can still use sanitizers. There's a nice repository, a nice guide that explains how to use sanitizers, but obviously sanitizers only check this run on this architecture. So what people do is trying to load some other programs or trying to use your plugin heavily or so, but yeah, it won't guarantee that it's fine on another architecture or something. So we also have tools like Miri. It's a detection tool for undefined behavior. It's especially nice if you have some unsafe code in your Rust to increase performance. And it can check out of bounds memory access, use after free, data races, memory leaks. But for me, the coolest tool I discovered was Loom. This can check atomic and thread synchronization. And this really checks your assumption for every allowed value that an atomic load could see on every architecture. So if it runs through Loom, you can be really safe that it will run on every case. It's still quite easy to set up, just check their tutorials, but there are also some limits, like it cannot check every type of reordering for relaxed. That's just not easily possible to reorder the code in any way in the implementation, and it can have false positives with sequentially consistent. But especially for acquire release, it works completely. Yeah, then there are some audio crates I want to recommend, like Rubato is for real-time resampling or offline resampling. It's very nice and has a lot of different options, so FFT-based resampling and just like sync interpolation that you also can change in real time by just changing the value as often as you want, the resampling factor, so you can use it for pitch shifting and stuff. Then for FFTs, there's Rust FFT, which is SIMD. So the performance is very powerful. You have Neon, SIMD, and AVX2. And Real FFT and Easy FFT are just wrappers around Rust FFT that makes it easier to use. Complex to Real or Easy FFT is nice for tests because you don't have to set up all the FFT scheduler and so on. You just have one function and it has traits, so you can just call .fft on your vector and you will get the complex vector out of it, but it allocates memory. Then Babycat, for example, is the easiest to load any audio file, and there's integrated resampling. But if you want to go lower level, you can use Hound, what is for WAV file I/O, and Symphonia is an amazing crate to do audio file decoding and disk streaming. It can decode most of the audio files like AIFF, FLAC, MP3, WAV, and many more. But there's no encoding built in this library, so only decoding, only reading audio. Yeah, if you want to check out a little bit of my work, I published some crates on NeoDSP, and there's my contact information. I just check in. We have 7 minutes left, I guess. Is this enough for questions? So yeah, just write me a mail or add me on GitHub or LinkedIn. And if you ever have some Rust questions, feel free to hammer me. Thank you very much.